Hi everybody, welcome back to the channel. In this video we're going to take a look at something called indeterminate forms and something called L'Hopital's rule, which is going to be a rule that helps us be able to deal with our indeterminate forms that we're going to see. To get started, let's go ahead and look at an example that's going to motivate why we're looking at this. Let's start out with something like the limit as x goes to 1 of the natural log of x divided by x minus 1. Now, you might have some strategies for how to deal with this at some point. Probably you'd think about trying to plug in the value of 1 for x if you could. The problem with that is the natural log of 1 on the top is 0, and then 1 minus 1 on the bottom is also 0. So when you plug in 1 for x, or if you try to plug in 1 for x, you get 0 over 0. And you may have a strategy after that. You may try to simplify. What should look pretty obvious is that it's not really easy or even possible really to do much to simplify the natural log of x divided by x minus 1. That's already pretty simple. You might have another strategy that says something like try to plug in a value for something close to 1, like 1.1 or 1.01, and just try to understand what's happening as x gets really close to 1. The fact that you get 0 over 0 here could potentially mean that there's a hole. But remember back when we talked about limits, we didn't really have a problem if there was a hole. That's okay that there's a hole. If all it is a hole here and not a vertical asymptote, then we can still deal with that. But we haven't seen a problem like this with logs or with other functions where we get 0 over 0. The only thing that we've seen in the past is polynomials where you get 0 over 0, where you might be able to factor or simplify or cancel somehow and get to a point where you can plug in. But that's not the case here. Okay, so we need a new method. And there are actually going to be what we're going to call 5 indeterminate forms. The idea of an indeterminate form is that we don't know what we always get. For example, part of the reason this is a problem is because when you think about 0 over 0, this sort of seems to break some of the rules that we think we know from our past. For example, some of you may be thinking about how 0 divided by anything is supposed to be 0. But what you may not remember from when you learned about that idea of 0 divided by anything is 0 is that there's actually kind of a disclaimer in there. And the disclaimer is that 0 divided by anything that's not 0 is 0. And you may remember something else that says something like any number divided by itself is supposed to be 1. But there's a disclaimer in that rule as well, which is that as long as the value you're talking about is not 0, you may think about anything divided by 0 is supposed to be undefined. Well, yeah, sort of, but as long as what's on the top is not 0 as well. So there's all these kind of caveats in here about how you kind of can't get this situation. We've kind of avoided this situation for years and kind of stepped around this and said, well, the exception is when you have 0 over 0, and we really won't talk about that. And the reason why you haven't talked about that in your past is because you need calculus in order to be able to do a problem like this. And what's interesting here is that in order to talk about derivatives early on, we needed limits. But in order to talk about limits in this case with these indeterminate forms, you need derivatives. And so it feels a little circular. You need limits for derivatives, you need derivatives for limits, or at least in this case. So I will say that this section in the book is a little bit oddly placed. We've been talking a lot about derivatives, and then now we've been talking about a lot of applications of derivatives. And this is an application of a derivative, but it feels a little bit weird because we talked about limits like 2 chapters ago, and now we're kind of jumping back into limits for this one section just to see what happens with this weird indeterminate form case. So let's take a look at our five indeterminate forms. And here's what I would say about this. If you ever see any of these forms, you shouldn't automatically have an idea of what is going to happen. You should be able to say, well, I really don't know what's going to happen. Sometimes you do get 0, like having 0 divided by some number, but sometimes you do get undefined, but sometimes you get 1, and sometimes you get 7, and sometimes you get pi, and you just don't know what you're going to get. You actually have to know exactly what the function looks like that you're starting with, and what the limit is that you have. What is x approaching? And so here are your 5 indeterminate forms. If you see any of these, don't say, I know exactly what's going to happen. You're going to need to use the rule that we're going to talk about in a minute. So the first one is 0 over 0. The second one is a lot like 0 over 0. In fact, it's really easy to manipulate infinity over infinity and turn it into something that looks like 0 over 0. What we're actually going to see is with L'Hopital's rule, you don't necessarily need to do that because L'Hopital's rule kind of touches and hits both of these two cases of 0 over 0 and infinity over infinity. So we're going to actually take all the other cases and try to bring them back to look like one of these two forms. But here are the other three. So the other three look like 0 times infinity, 0 raised to the 0 power, and infinity minus infinity. So these are really weird. Let me just give you one case for this last one, because again, we haven't really seen these a lot, so I think students tend to think, oh, I know what that's going to look like. And the common answer that I get is when you look at infinity minus infinity, of course, that's something minus itself, so that's going to be 0, right? Like that. Is that equal to 0? And again, it's not always equal to 0. Sometimes it is. Sometimes it's equal to infinity. Sometimes it's equal to 1. Sometimes it's equal to 7. And so here's kind of the situation that I'll give. Think about taking all of the natural numbers. How many natural numbers are there? Okay, there's infinitely many. Natural numbers meaning start at 1, 2, 3, 4, 5, all your kind of positive counting numbers. Now, think about all of the even positive numbers. How many are there? There's actually infinitely many. Okay, and so take all of the natural numbers and remove all of the even positive numbers. What do you have left? Well, you don't have 0. You actually have all of the odd positive numbers. How many are there? Infinitely many. So you really just don't know what you're going to get from knowing that you're taking infinity minus infinity. It just depends on the context that you have and what situation you're looking at. But the goal is going to be to take all of our cases and turn them back into this 0 over 0, or I could say the infinity over infinity case. We're going to try to manipulate all three of the other cases and turn them into 0 over 0. The turning them into 0 over 0 is not actually going to involve any calculus. That's just going to involve some algebra. But then once we have it in a form of 0 over 0 or infinity over infinity, then we're going to bring in some calculus. Okay. So here's what here's what L'Hopital's rule says. All right, it says, suppose f and g are differentiable and g prime of x is not equal to 0 on an open interval I that contains a, except possibly at a, because remember there could be a hole, and the limit would still exist if there's a hole. That's okay. The first part is just some wording, basically saying that if f and g are both differentiable, if the derivative exists for both of those, and we need g prime of x to not be equal to 0 because that's going to be on the bottom of a fraction. So it can't be equal to 0 as a function, like it can't be the 0 function. Notice it doesn't say what x is. We're not plugging in a specific value of x. We're just saying g prime can't be equal to 0 as a whole. So here's really the important part. Let me put it in kind of a different color. If these two things happen right here, or I should say one of these two things happens right here, basically if the limit as x goes to a of f of x is equal to 0, and the limit as x goes to a of g of x is equal to 0, or it says that those could both be going to infinity. Here's another way to think about this without a ton of wording here. The top case basically says if you get 0 over 0, or if you get infinity over infinity, then you can apply this. That's kind of what this is saying. So if f and g are both differentiable on an interval, and when you take the limit as x goes to a of f of x over g of x down here, if that gives you 0 over 0 or infinity over infinity, then what L'Hopital's rule says is that all you actually care about is the derivative of f and the derivative of g, and you take that limit. So in other words, the limit as x goes to a of f of x over g of x actually ends up being equal to the limit as x goes to a of f prime of x over g prime of x. Now, the reasoning behind this is a little bit interesting. Think about as x goes to 2, for example. As x goes to 2, we want to know what's happening to the limit. But to look at what's happening to the limit, we can really look at the speed at which f prime is going to a specific value, or g prime is going to a specific value. And so really, or I say specific value, but really I'm talking about the specific values of 0 or infinity. So let's look at an example to kind of motivate this. So let's say we have a function x, so y, this is y equals x, and the function y equals x squared, which looks like this. Okay, and if we look at which one, let's talk about the limit as x goes to, and earlier it said a, but we could also use infinities in there. So what if we use the limit as x goes to infinity of x over x squared? Okay, this is a case where if you try to think about plugging in infinity, again, whatever that means, we get something like infinity over infinity. But the question is, how are they growing? What are their speeds? How fast are they going to infinity? Okay, if you kind of blow this up and look at it on a big picture, I think we can all agree that y equals x squared is blowing up and going to infinity a whole lot faster than y equals x is. Another way to think about that is when you as x gets bigger and bigger and bigger, this space in between the two functions is going to get massively tall. Okay, and so y equals x squared is growing a whole lot faster, which I know you can cancel an x on top and bottom, and this is the same thing as saying kind of 1 over x. And so you should end up getting 1 over infinity, which is 0. But we can find that if we use L'Hopital's rule there as well, right? So L'Hopital's rule says if you get infinity over infinity, which we do, then go ahead and take the derivative of the bottom and the derivative of the top and the derivative of the bottom here, and look at that limit. And so we can take the limit as x goes to infinity of 1, because that's the derivative of the top, and then the derivative of the bottom is 2x. And these are supposed to be equal using L'Hopital's rule. And so again, if you plug in infinity over there, you again get 1 over infinity, you end up getting 0. And so the idea of using L'Hopital's rule, though, says how fast are your functions growing? Is one growing a lot faster than the other? And so whichever one is growing a lot faster is typically going to kind of dominate in the long run behavior, or with your limit here. But when you're talking about functions, you don't need to just be talking about as x goes to infinity. It could be as x goes to a specific value a. So let's look at the one function we started out with at the beginning. We had something like this: the limit as x goes to 1 of the natural log of x divided by x minus 1. And what we said is if you try to plug in 1 for x, you get 0 over 0. And I don't know, one thing you could do is you could grab your calculator over here and you could go plug in the function natural log of x divided by x minus 1. I'm curious if anybody did that and goes and sees what happens as x approaches 1. You actually get a little hole in there. And so here's by the way, some notation that I like to use. When you see the limit as x goes to 1, you get 0 over 0. Instead of just saying, okay, cool, because that's equal to 0 over 0, we get the limit as x goes to 1 of the derivative of the top and divided by the derivative of the bottom. That's true. That's what we are going to do with L'Hopital's rule. I like to put a little LHR here on my equal sign, just so that I know why they're equal. Because if I just write a couple of steps here and say the limit as x goes to 1 of the natural log of x divided by x minus 1, oh, that's equal to 0 over 0, and then in the next step I write equals the limit as x goes to 1 of 1 over x divided by 1, which is the next step based on L'Hopital's rule. That's the derivative of the top and the derivative of the bottom. If I just write that and don't have kind of this LHR in here, what tends to happen is students tend to look at this, and myself included, look at this sometimes and say, how did I get there? Like, how did I make the jump from here to here? And so I put a little LHR in there just so that I know, why are those equal again? Oh yeah, that's what L'Hopital's rule says. And so now you can go ahead and plug in the value of x equals 1, and you should get something like 1 over 1 or 1 as your answer. Okay, so just because we get 0 over 0 or infinity over infinity doesn't mean we can't handle it. Hope you've enjoyed the video.